Cybersciences at Augusta University, and I'm going to talk to you about my approach to handling code. And my point of view is that you've got to document code extremely thoroughly for several reasons. Helps you understand how the code works, helps you debug it, helps you analyze it. Okay, and I'll give you a couple of examples, a couple of case studies. Now, we all know that code is notoriously difficult to get right. Let's review why that's so. One of the main reasons is code is discrete and behaves in a discontinuous manner. Okay, if I scrape a few molecules off this code, it's not going to collapse in a heap. But I can change one line and a 50 million line operating system, and if it happens to be the right line, the whole thing can come crashing down. Okay, so that's a real problem. Okay, code is really, really hard to get right and secure because of this. Because it's random, unpredictable, discrete. Okay, so it doesn't have the nice properties of continuous systems. Okay, buildings and bridges can be over-engineered for safety. You just make the I-beams bigger and thicker. You make it handle 50% more than the expected load, and you're good to go. There is no such technique for software. Okay, there are some things like triple modular redundancy. These handle in some cases, but if you've got three systems running the same software with the same inputs, you're going to get the same bugs. So, okay, and furthermore, there's a huge semantic gap between what the code, how the code reads syntactically, and what it does at runtime. And that's a much bigger gap than again you have with physical structures. And we've got a bridge. You know, it's known what the bridge is supposed to do. If you've got a building, it's known what the building is supposed to do and how it will behave from the physical structure itself. With code, that's not true. Okay, there are well-known examples of 5-line programs that no one knows how to analyze. Okay, there are open problems in mathematics. Okay, so this semantic gap between what the code looks like and what it does at runtime is responsible for bugs, security bugs leading to exploits, okay, which some have been in the news recently, like the CrowdStrike bug. Okay, and we just learned that all of our social security numbers have just been swiped. Okay, and you get that dreaded letter. We value your privacy, and we all know what that means. Okay, no you don't. If you did, you'd engineer your code properly. Okay, failures in deployed systems, I mean, just go to the com.risks news group, tons of those, cost overruns, missed deadlines, etc. Okay. So, a long time ago, Vic Basili and Richard Selby established that just reading code was more effective than testing code. Okay, this was a landmark study, and this was quite unexpected. Okay, professional programmers reading code did better than running code at finding bugs. With students, there was no difference, but with professionals, there was. Okay, now of course, back in '87, code bases were a lot smaller than they are today. Okay, other studies have shown that thorough documentation helps with code reviews, and other studies show that, well, code bases are so large these days that traditional code reviews are losing their effectiveness. Okay, so how to document? Well, you've got to document hierarchically at many levels of abstraction. Okay, because code is just so hard to understand and it's so big, you've got to start with the big picture and gradually refine it. Okay, you've got to maintain consistency between these abstraction levels. This can be automated to some extent. Okay, so we my software engineering students last semester constructed an environment in which this is done to some extent. You can track changes, and you can use large language models to check semantic consistency between these levels, okay? And that helps you maintain a mental image of how the code works. Okay, so at the top tier, you've got to have a block comment for each class. What does it do? Purpose of the class. For each method, again, a block comment telling you what the method does, constraints on inputs, and what does the method actually do. And this is still not standard practice. I mean, one of my examples is a block of code from a PNG processing utility, and I downloaded the main file, and you go through it, and for every method, there is no comment telling you what the method is supposed to do. So how are you going to figure that out? Yeah, by reading the code. Okay, so that takes 100 times more effort than reading a 2-sentence description telling you what the method's for. Okay, the second tier should be a code sketch, which gives you basically at a high level, here's the algorithm, expressed mostly in words. If you can't express your algorithm mostly in words, then maybe you don't know what you're doing, or maybe you don't have a really clear picture of how your code is supposed to work. And then the third tier is inline comments that are more detailed and talk about the data structure of the algorithms, and further levels until you get to something where the relation between the comment and the code is pretty clear, it's pretty straightforward. Okay? And you may need more or less levels depending on the complexity of what you're dealing with. Okay. Tony Hoare, well-known computer scientist. There are two ways of putting together software. Make it so simple there are obviously no errors. Make it so complicated there are no obvious errors. Okay. The code sketch is inside every large program there's a small program so I can get out. Okay. The small program is what your code sketch should be. Express the key algorithm without the coding details. Okay. There are two separate tasks in putting software together. The key algorithm and then the coding details. Those are separate tasks. They should be done separately. If you do them at the same time, you're just making things harder on yourself. Okay? So, have a code sketch that tells you how things work. Okay? That helps developers understand the code. You read the code sketch, and now you're prepared to actually go in and handle the details of the code. It helps you maintain the mental image and helps with the cognitive workload. Okay, so we have a tool that does this, and you can invoke an LLM, etc., for consistency checking. Okay, so I'll go out of the presentation so I can show you. Here it is. So here's a method. Okay. Requires W is not null, modifies this, okay. If W, okay, otherwise modifies this to process a query for an additional keyword, okay. This is a matching document search engine, and you're adding keywords, and it tells you how it adds a new keyword. It finds the documents that match the additional keyword and adds them to the set, okay. Here's the code sketch. If I click on each line in the sketch, it takes me to the part of the code which is responsible for implementing that line. Okay, so you can read this simple English and you get a good picture of how the overall code works. Okay, one of these comments is sufficiently challenging that it's refined into a second level. So again, you can read this, it's easier to read than actual code. Okay, we'll go back to that was just a preview, just to give you an idea of where I'm coming from. Okay, I use LLMs to relate comments to code because comments are natural language. So you need something like an LLM to handle them. You can't use a theorem prover. Okay. You can check if code and comments correspond. You can check if a high-level comment and a more detailed comment that refines it correspond. Aids with debugging. So in some sense, it's a form of validation and verification of the code. Okay. Now, we've all heard a lot about using AI to write code, to analyze code. Now, if you use AI to analyze 1 million lines of code in one shot, you've no idea if the result is good or is nonsense. You simply have no way of knowing. You're going to go read 1 million lines of code, okay? Or if you use it to write 1 million lines of code, same problem, okay? When you're using LLMs on huge code chunks in one shot, you've simply no way of verifying if they're telling you something reasonable or if it's way off, apart from manual inspection. Well, if you're going to do manual inspection, it's got to be on pieces of code that are cognitively available to you, that you can actually look at and understand. Okay. So you've got to do it on small chunks of code, but it's still saving you a lot of work. Okay. So there's no free lunch. Okay. There are 4 ways of using our tool. Correctness and refinement are the ones we've explored most often. Correctness, a code implemented in a sketch. Okay. Better description is obtained with, if you add comments, you get a much better result than without comments. Okay. Refinement, check that more refined documentation is a correct refinement of coarse or high level documentation. Write code that implements a code sketch. Okay. If I give it a method and I just give it a statement of what the method is supposed to do and I tell it to write the code, you'll get pseudocode. If you give it a code sketch, you'll get actual code. Okay. So that's one way of getting actual code. You've got to give it you've got to give it the output, and you'll get code that's sensible. Okay. If you just tell it, oh, here's what this method is supposed to do, it really won't generate decent code. Okay. You can use it to summarize. Given code, summarize it. Okay. That also helps. Okay. We mostly used Claude, and subsequently I've used ChatGPT. So far I've gotten somewhat better results with Claude. Okay. We implemented this in IntelliJ, and because that gives a very nice public API that we can use. Okay. Our system parses and identifies comments, stores comments in a hierarchical structure, and you can highlight, navigate like I just showed you, and it interfaces with the text editor, okay, of IntelliJ. Okay, so you've got modules for parsing and managing the code. Okay, so each comment is an entity by itself. It can have children, okay, and you have pointers and patterns and text ranges for storing the part of the code that implements that particular comment. So I can click on the comment in the code sketch and it will highlight the code that is responsible for implementing that comment. And that's really important because that lets you relate some comment in English, hey, do this or do that, do whatever, and it will take you directly to the code that is responsible for doing that. Okay? So you can navigate from code to comment back to the code. Okay? So that helps with just manually checking that the code corresponds in a way that makes sense to the code sketch. Okay. Straightforward structure for implementing this. Okay. There are 2 case studies, buffer overflow in PNG processing and document search engine. Okay, so PNG files contain a bunch of chunks for storing various properties like color palettes and transparency information, the ones we'll be interested in. There's many others, of course, and also chunks that contain actual pixel data for the image. Okay, so I took a bunch of code from the PNGR util file. Okay, this has almost no comments whatsoever. I mean, it has a few comments here and there. But again, I mean, and this, in my humble opinion, is a huge problem. Okay, here it is. Okay, you can just see occasionally there's an odd comment, but most of the code is uncommented. Here's a method header. Okay. Okay, doesn't tell you what the parameters mean. Okay. Right. Some methods, their functionality is described here. This is a huge problem. Okay. This, in my opinion, is responsible for a lot of the problems in systems. That people come back and read the code 6 months later and they just don't know how it works. Okay, so here is the here's the code. Basically, this line checks if a palette chunk hasn't been seen and issues a warning. Okay, because you're supposed to count a palette chunk before a transparency chunk. Okay, so this is invoked when you've seen a transparency chunk. If you haven't seen a color palette chunk, that's an error. Otherwise, check if LNG is the length of data that you're reading in. If it's larger than the number of palette entries, then that's an error. Okay, you're reading this into a buffer. If this is too big, you're going to get a buffer overflow. Okay, so you check for that and issue a warning and return early. Okay. After the if statement, you actually read length data into the read buffer while updating the cyclic redundancy check. Now the problem with this, when buffer overflow happens, is if the if condition is true, you issue a warning, you skip the else, and you come in and you do this read, and length is on the check. Okay, so if length is too big, you get a buffer overflow at this point. Okay, the if branch inspects, checks if there's a PLT chunk, issues a warning, and continues. The else branch checks the amount of data being read in. Okay, it's used in either case to set the amount of data read into the buffer. Okay. Now, in running LLM queries, I discovered a bunch of interesting things. First, if you repeat the same query, the answer will change. Okay. The reliable answers are when they stop changing. Okay. Sometimes you get into a situation where it keeps changing its mind. Okay. So I ran it 5 or 6 times. It helps to delineate the code and the code sketch carefully, because on one occasion it took the first line of the code and treated it as if it was part of the code sketch. Don't use proper words for identifiers. Okay, this is kind of a pet peeve of mine. Okay, so in the actual PNG file, LNG is actually written as length. But then if I'm describing the code, the word length can either mean the identifier or it can mean I'm describing length. Okay, so that's confusing to humans, and it's also confusing to LLMs. Okay, state assumptions. Okay, so here was the query I used. Is the code below susceptible to a buffer overflow? assume that the number of palette entries is less than the max. Pay particular attention to control flow. Okay? Why is that assumption important? Because the buffer is declared to be of size maximum palette length. Without telling it that, it starts worrying about the buffer being too small, rather than length being too large, and starts giving you problems that don't exist. Okay. So, first time around, it says code is not susceptible to a buffer overflow. Okay? Therefore, when this is called, LNG is guaranteed to be less than to the size of rebar. Okay. Basically, it doesn't. It acts as if the else branch is being executed always. Okay. Second time around, I believe this code is potentially susceptible. The critical issue is the control flow. Okay? It's not been seen. This code will only issue a warning and continue to execute. Okay? And so if this is larger than max palette length, that will cause buffer overflow. Okay, so second time round it gets it. Okay? It suggests a fix. The fix is, well, if you do this warning, return early. Okay. But hey, we don't want to return early. What we want to do is check this always. Okay, so it's the wrong fix. Okay, diagnosed the problem, but it didn't find the right fix. Third and fourth responses, they changed the else condition to this, but that still doesn't fix the problem. Okay, the fifth response doesn't change the original code, but adds this, which also returns early, and again, that's not what we want. Okay? Okay, and the sixth response just basically adds an early return in the original if branch, as well as this. So again, none of these are correct fixes. So, instead of asking it, is it susceptible to overflow, I give it a code sketch and tell it, okay, check if, I'm going to zoom out. Okay, so here's the code sketch. Create a buffer. If a PLD chunk is not yet exceed, issue warning. Okay, if the LNG is larger than the entry, issue warning and return, and then we use the buffer. Okay, so in the code sketch, I basically have two ifs instead of an if else. Okay, so the point is, it's much easier to write a code sketch that expresses the correct algorithm than to write code that expresses the correct algorithm. Because you're not bogged down in the details of coding, you're just thinking at a high level. Okay? The code is the same. Okay, that's just a review. Okay? And now, basically, I ask it, is the code the correct implementation of the given code sketch? Okay, again, with the same assumptions. Okay? And the first time around it says, yes, it's fine. Okay, which is obviously wrong, because the code sketch is if followed by if, and the code is if else. Okay. Second time around, I apologize for the font being so small. Okay. Right. Again, and these are just fragments of the answers. These checks are combined into an if-else-if structure. Okay, the change means that the PLT chunk hasn't been seen. First, the second check will not be performed. Right. So now it gives you the correct fix, which is one if followed by a second if. Third response gives you the same thing. Okay, the verbiage is a little different, but the code is the same. Okay, fourth, fifth, and sixth responses, same code fix. Same general verbiage. I mean, the words are a little different, but basically you've converged to a fixed point. Okay, and that's good. Okay, so you get much better convergence with comparing with a code sketch than you do just giving it a piece of code and saying, hey, is this going to overflow a buffer or not? Okay, where you saw that it just bounces around between different ideas. Okay, here it converges. Right. When I ask it, is it to settle to an overflow, it says, yeah, it eventually says yes, but the fixes keep changing. Here, the fix becomes the same. Okay, it converges to the same correction to the code quite quickly. Okay, so that's why it's important to have a code sketch, because it guides the LLM, it guides the search for a correct debugging of the code. Okay, it converges more often, converges faster, the code sketch guides, and the code sketch is more intuitive and easier to understand for a human. Okay? Right. ChatGPT gave similar answers when I asked it to check buffer overflow, but it did not detect a discrepancy versus code sketch. So that's kind of interesting because it means that use multiple LLMs, don't use one. One might do a lot better than the other. Okay. Another thing you can do is refinement. Okay, so again, this is from the document search engine, which I'll discuss next. Okay, so this is this is aligned with the code sketch, and this is a more detailed refinement of that, and it will actually tell you, yes, it maintains the essence. Okay, so this is nice, because effectively you're coding in English, which is, and eventually turn to actual code, but you can code in English, and that's a lot easier than coding in code, because you can just think about the algorithm without worrying about the details. Okay. The second case study is a document search engine. Okay, so you've got a collection of documents to be searched, okay, which basically are input for all methods. Documents can be added. Each document is a type and a body, which is a sequence of words. And you've also got a sequence of queries. Each query is a single keyword. And what you want is you want to list of matching documents ordered by count. To match, a document has to contain all the keywords. Okay, and each keyword must occur at least once. And you want to count the total number of occurrences of all the keywords and sort the documents by this total occurrence count. Okay. Another key thing to document is data structure. That's crucial. Okay? So Linus Torvalds, bad program to worry about code, good program to worry about data structures and their relationships. Because after all, the only purpose of code is to manipulate data. That's the only reason it's there. Okay. So what's the data? Okay. A document is the type of a body. Query is an ordered list of documents ordered by occurrence count. And in addition, we've introduced something called the word table, which is a hash table mapping each word W to a list of what are called doc count objects, DC, which tell you that W occurs C times in document D. Because when you're doing these searches, every time you get a new keyword, you don't want to do a linear scan through all the documents, okay? Right? If Google worked that way, you'd die of old age before the query came back. Okay, so you want to summarize occurrence information in a hash table for fast lookup. Okay, so this is the top level module that organizes everything. This is the query class that maintains the current query. Okay, this is the word table that maintains the hash table, which tells you for each word what documents it occurs in and how many times. Title table maps titles to documents. Okay, that's the class that maintains a document, which basically has a iterator that gives you the next word of each document, and a method for giving you the title. And these are doc count objects, which are pairs of documents and positive integers. Okay. The engine class implements the user interface. You've got a query, a word table, and a title table, a constructor to start things off, and start the query with the keywords, add more keywords, and add new documents from a given file system. Okay, so construct a new query object, add a new keyword. So notice, input and output. Describe the inputs, describe the outputs. Okay, so the PNG file I just showed you doesn't do that. Okay, I mean, I'm looking through the method that I got my block of code from. Oh, it has length parameter. Oh, let me look up the comment. Surely it will tell me what length means. No, it doesn't. So you have to scan through the entire piece of code to reverse engineer what the length parameter actually means. Okay, that's a huge problem. I mean, this was known like 40 years ago. You should be doing this. Still not being done. Okay, query more. Okay, so query first. Your input is the word table is always an input. A keyword W. The output is a list of documents that contain this initial keyword ordered by occurrence count. Query more and a new keyword WK to an existing query W words 1 keyword 1 to K minus 1. Okay, and you've got the documents matching so far and the new keyword. The output is an updated list of documents that also match the new keyword, and now you've got to reorder them by the total occurrence count with the new keyword taken into account. Okay, and finally, adding a document from a file. When you add a document, you've got to update the word table. You give information about every word in the document, how many times it occurs. Okay, and if there's a query in process and the added document is a match, you want to add that to the list of matches. This can get a little complicated. Okay, the query class contains a word table, matches, and keys. Okay, and a constructor and methods to add keywords to an existing query. A constructor that kicks things off with when you start a query with a single keyword W, and then adding a keyword, adding a document, and then simple getter methods. Okay. Major methods: query again, input and output, add key, add new keyword, output matches, add a document. Okay, so these are similar to the engine method, because they're basically they implement that. Word table contains a map. It's a hash map, mapping equal to W to a list of document and count objects. Okay, the constructor creates a new word table, and you add document and you look up a given keyword K. Okay, uninteresting words need to be marked. Words that you never want to use, like the. Okay, you never want to use that as a keyword, so you mark those and you exclude them from queries. Okay, add interesting words of the document D to the map. Okay, initialize the word table. Okay, add a document, go through the document for every word in the document, add it to the map with the number of times it occurs. And for a given word W, tell me all the documents that it occurs in and how many times. Okay. So code sketch. Look up W in the word table, sort the matches. Okay, when you're starting a query, it's easy. Because I look up W, I'm going to get an array list of all the documents that W occurs in together with count. Sort that on the counts, okay? It's very simple. Adding the word W is a little more involved. Add W to keys. Keys is the array, an array of strings, giving you the list of keywords. Look up WK in the word table. Now, for each document, right, so now we have the new documents that match the new keyword. You got to intersect them with the existing documents to get the new matches. Okay? Now, in order to do this efficiently, we're going to put the new documents into a hash table, because otherwise if I have two lists and I'm intersecting them by using linear search, the runtime is quadratic. Okay? With these titled as lookup table. Each current match, look it up in the hash table. If it's there, that means it matches the old keywords and the new keywords. Store in an array list and update the occurrence count to include the number of times the new keyword occurs. You already have the occurrence count for keywords W1 through K minus 1. You just add the occurrence count for WK. Once you've gone through all the current matches, you resort the array list. Okay? Notice how easy it is to discuss this. We figured out the algorithm. There's no code involved, no identifiers, well, a few, but nothing like the level of detail involved in actually writing the code. Okay? You figure out the algorithm, then you write the code. Okay? Adding a document, well, you've got to know the number of occurrences in the document of all the keywords. Okay? So you go through the existing keywords in the query, W1 through WK, check them all. If they all occur, add D as a match, and insert it in the right place. Okay? If some keyword doesn't occur in the new document, then you leave things unchanged. It's not a match. Again, this can be discussed easily at this level. Okay? Here's the code sketch. I showed you before. Here's the actual code. Okay? I run it through. It says, okay, so generally follows the structure. There are a few discrepancies. There's no null tag. Sorting the matches did not mention. Doesn't mention the sum of occurrence count. So, okay. So generally matches, but this, again, this gives you, okay, it gives you some feedback for improving your code sketch. Okay? And that's also valuable. Okay? Here's another one. What I did here is I flipped the not B to a B. Okay? So here I'm going through checking all the keywords. If each keyword occurs, I simply add it into B. So if B is initially true, and I check if each keyword occurs. If B remains true, that means they all occur. If I get a false back for any of the keywords, B becomes false. Okay? So if B is false, you return because it's not a match. Right? So in the correct code, B should be false. Okay, so what I did is I changed it to a not B. I changed the not B to a B. Okay, just to see if, okay. Here it says earlier call keywords are found contrary to the stated intention, the initial Boolean text of the inversion. Okay, so it finds the problem. And it actually tells you if, gives you the code if not B. Okay, second response, same thing. I ran the query again, okay. It's still telling me basically the same thing, so that's good evidence that it's better. Okay, here's the interface. Well, this is it. Okay, so this is the query class. So you've got a block comment at the top, telling you what the class is about. Here's the query method. So, okay, so you've got code specification comments and then code sketch comments. So it requires the pointers are not null, makes a query for a single keyword, helps the engine query. Okay, set keys to the single string W. Okay, keys of 0 is W. Lookup key W in the word table by invoking W to lookup. Matches equals k.lookup. Sort matches. Okay, collections.sort. Okay. Oh. Yes. Whoops. I need to go out. Presentation mode. Okay. Okay. So here's the code sketch. So starting a new query, okay, it requires pointers are not null, makes a query for a single keyword, and helps the engine query first, okay? A help statement tells you where it's being called from, okay, which is useful in tracing code. Okay, set keys to the single keyword string W, that's done here. Keys of 0 equals W. Look up the key W in the word table, matches equals K lookup. Okay. Sort the array list, collections.sort. Okay, that's quite simple. Setting up an initial query is straightforward. Adding a key is more complicated. Throw exception if W is not a valid key. Okay. Right. If there's no query in progress, you throw an exception. If W exists in the existing keywords that have already been submitted, you throw an exception because you're not going to repeat the same keyword. Okay, add W to key. That's basically, well, just copy everything over and add W, create a new array list that's one bigger, copy everything over. Okay, these are, you know, the array of keywords is small, so a linear time method is fine. Okay, look up W in the word table and store the information about matches on W in a hash table H. Okay? Okay, for each document in which W occurs C times, store DC in the hash table H with these titled as a lookup key. Right? So this actually needs a level 2 sketch. Okay, this helps. Okay, so here's the list of looking W up, declare a hash table H for each element in this list, store it using d.title as the key. And here's the corresponding code. Now, you look at this, you look at that, and you can see, yeah, this code really does implement that sketch. Okay, it's easy to see. And you can run all the levels through the LLM, right down to this versus the code, and it will confirm that each level is a correct refinement of the previous level. Okay, and finally 1.3. Okay, for each code sketch, look up the document in the table H. If it's there, store it in an array list. Sort the array list. Okay, so I'm going to take each document that is an existing match to the keywords 1k minus 1. Does it also match the new keyword wk? If so, it's an overall match. Put it in an array list with the updated occurrence count. And again, it's just easier to think about this. At a level of a code sketch. Okay, there an array list for each current match, each document with its total occurrence count in the matches array. Look up its title in the hash table H, which tells you, gives you information about the new keyword W and how often it occurs in documents. For matches on W only, okay? Right, so if the document occurs in, W occurs in the existing document that we're looking at, then update the occurrence count of the document to that's how often the previous keywords occurred, and add to that the number of times the new keyword also occurs. That's the new updated total occurrence count. Okay. Otherwise, if the document doesn't occur, do nothing. Okay. When you're done with all of that, sort on the count field. And here's the actual code, and again, it's easy to check that the code actually corresponds to the code step. By the way, when I gave it this and I told it to synthesize code, it produces code that's roughly like this. Adding a document, that's also complicated. Okay, requires document is not null, and H maps the words indeed to integers. Notice it requires a hash map that gives me occurrence information for the document itself. Okay? In fact, if each keyword of the current query is in the hash table H, then D is a match added to the existing matches. Okay? So, if the map print D contains all the keywords, that's a typo. Compute the total occurrence count sum and insert D with its occurrence count into the array list of matches, otherwise it's unchanged. Okay, and again I can click on each line in the code sketch and it will take me to the part of the code which implements that line. Okay, so first I check if every keyword is contained in document. So I go through all the keywords and I check if each key occurs in the hash table. If so, B remains true. If not, if B becomes false, I return error. Okay, this was the chunk of code that I showed you earlier being checked. Okay, now B contains all the keywords, update matches as required. So again, if I'm coming from here, it'll take me here, compute the total occurrence count. I go through all the keywords and I just look up from the hash table how many times each keyword occurs in the document and I add it into the total. Okay? I create a new pair using the document with its occurrence count. I insert it into the list of matches and I resort the matches. Okay? When I wrote this all up, and I just did comments manually and I ran it, there was one bug. The bug was at some point I wasn't updating a variable. Okay, there was a missing assignment statement. just before return. So the updates won't be reflected in the final version. That was it. Okay, just one bug. Okay. Similarly, okay. So that's my vision for how these things should work. Okay. Future work. You know, automation for frequent small-scale reviews, track design and code changes, flag them very quickly. If you change code that corresponds to a comment, put up a red flag or highlight the comment in red or something. Say, hey, the code changed. You need to revise the comment. Okay, if a code sketch comment changes in the code, notice that the code sketch lines have two occurrences, one in the code sketch, and then I copy the same line down right in front of the code that implements it. If you change one of those lines, it's got a flag to change the other to keep them consistent. So there's all sorts of consistency checking that can be easily flagged, and that I think would be quite helpful in developing actual code and keeping it consistent. Okay. If code or documentation impact other areas, you can follow call chains or do data flow analysis. Okay. I still remember when I was a grad student intern, I was given a whole bunch of code written in some version of Prolog, and for maintaining an object server, and I was told to go through and do some modifications. And I'm reading the comments to figure out how this thing works. And I'm looking at the comments, I'm looking at the code, and I go to the person who wrote it and says, hey, this comment is saying X, but your code is doing Y. And the response was, oh yeah, we stopped updating the comments like 6 months ago, we couldn't be bothered. At that point, I went to my supervisor and I requested a different assignment. Okay. Yeah. I mean, your own code is bad enough 6 months later if you haven't bothered documenting it, let alone someone else's. Yeah, another experience like that was we had this tool for visualizing concurrent programs. At some point, the person who wrote it left, and someone else took it over, and I went to the new person, I said, hey Charlie, it would be great if the tool would do this. And Charlie's response was, well, look, I'm not going to touch the execution engine because I don't know how it works. It's not documented, and if I even touch it, it's going to break. So don't even ask me for new functionality. Okay, and this is, well, that's what you get. Fred Brooks has pointed out that as systems age, the incidence of new bugs that are introduced by existing bug fixes keeps going up. It starts off as being 0.2. Now, for every 5 bug fixes, you get 1 new bug. Eventually, it becomes 1. Every bug fix introduces a new bug, at which point the system is basically unfixable. Provide the ability to track design documentation code changes frequently versus what is stable. Okay, stuff that's changing frequency is probably a problem area and should be looked at. Okay, or revisited and rethought. Okay. Engineering blueprint. Okay, if people built a skyscraper or a large bridge without very detailed blueprints, first of all, that tell you where every wire, every cable, every I-beam goes, how big and how thick that wire, cable, or I-beam is. If people didn't build these structures without such a set of blueprints, they'd be thrown in jail, okay, for criminal negligence. We build software like that all the time. And the way we build software is kind of like, I want to build a 100-floor skyscraper. Okay, let's get a good crew together, you know, roughly how big it is. I'll get my phone and say, okay, pour the foundation, you know what to do. You know, if there are any problems, we'll work them out later. After we put the frame together, we'll figure out where to lay the pipes and the electric wiring. Oh, we poured the walls, but we didn't put the pipes in. Okay, let's break the walls and put the piping in. Okay, that's how we put software together. Okay. It's only going to get worse. Any questions?
The one I was having was that, years ago, books like Code Complete stressed more the importance of doing better design work up front.
Yeah.
And looking at a lot of your kind of documentation ideas, you're kind of dealing a lot with just the standalone code. I'm just kind of curious, would it not be better to kind of a better link the code to the design of documents,
yeah,
and perhaps force more detail and with discipline into the design of documents, and so that really you're dealing with a complete package as compared
yes,
to maybe just.
Yeah, absolutely. I mean, the code sketch is essentially a design, but it's a design at kind of the sort of small, programming at the small level. Okay, yeah, there's also the programming in the large level, which obviously has to be dealt with. Yeah, so I'm starting with, okay, how do I handle one method, one class at a time? Now, once you've done that, how do I handle the system? Yeah, so yes, of course, this can be generalized to link design documents to code, maybe through hyperlinks or something. That's a much harder problem, but yeah, that absolutely has to be dealt with. Other things, use LLMs to handle, suppose I've got, a peer-to-peer system or some concurrent system that's tossing around crypto keys or something, okay? Can an LLM help me analyze that? Can it check for information leaks? But yeah, the design phase absolutely has to be dealt with in large systems. I mean, my actual areas are, I'm coming from a formal methods distributed computing background. So I'm well aware that in large distributed concurrent systems, you've got the design up front is really the main issue. But right now, we're not even handling small pieces of code. If you can't handle a small piece of code first, how are you going to handle a large piece of code? If you can't handle 10,000 lines properly, how are you going to handle 10 million? But yes, that is, of course, one of the next points in my agenda. How do we integrate design documents? Thank you for the question.